we just saw that one of the things we can do with an alternating series that converges is we can take a given partial sum and determine an upper bound for its accuracy, or an upper bound for its error, I guess I should say. Remember, the next unused term is always bigger than the error, right? So that's useful, but sometimes we want to say, well, I'm after an approximation for the converging value, and I don't want to stop until I get an acceptable error of less than, in this case, in this particular example, 1 over 1,000. This is the same thing. Where's my pen? The same thing as 1 over 1,000. Okay, so we're just going to keep on going until we get an error of less than 1 over 1,000. So we know that the difference between the actual converging value and the first partial sum, defined to be r sub 1, we know that's going to be less than or possibly equal to a sub 2. But we know what a sub 2 is. A sub 2 is 1 over 2 raised to the 4th, which is 1 over 16. And we know that 1 over 16 is, in fact, substantially larger than 1 over 1,000. So 1 is not enough terms to get the desired accuracy. So we're going to move on to r sub 2. R sub 2 is less than or equal to a sub 3. And a sub 3 is the same thing as 1 over 3 raised to the 4th, which is 1 over 81, which again is bigger than 1 over 1,000, so that's not enough terms. So we're just going to keep on going until we find, of course, there's probably a more efficient way, but we're going to try it this way. R sub 3 is guaranteed to be less than or equal to a sub 4, which is 1 over, let's see, we've got 16 squared is 256, which is still a fraction that is greater than 1 over 1,000, so that's still not good enough, so we're going to keep on going. R sub 4 is less than or equal to a 1 over 5 to the 4th, that's a sub 5. 5 to the 4th is 526. So again, we're looking at something that is too big of an error. This is an unacceptably large error. So we will go one more step, and we'll find that r sub 5, which is less than or equal to the 6th unused term, the next unused term, the 6th term, which is the next unused term, which is 1 over 6 to the 4th. Now, 6 to the 4th is 1296, according to my calculator. I don't have that one memorized, unfortunately. And 1296 is finally the first perfect fourth that is bigger than 1,000. So that means that this fraction is the first fraction that we find that is less than 1 over 1,000. So we now see that the fifth partial sum has a remainder that is less than the 6th term, which is less than 1,000. So that means that S sub 5 is the partial sum, the first partial sum that we can get to with an error of less than 1 over 1,000. It asks us to approximate it, so we'll go ahead and find out what it is. We'll let n equal 1 and go to 5, not all the way to infinity. We're just approximating this with 5 terms. And we'll do negative 1 to the n plus 1 over n to the 4th. And my calculator tells me that this is approximately equal to 0.9475. All right, so be careful. We found the 6th term was the first term that was small enough, so we used the 5th partial sum. That's because we're always comparing the r sub n value to the a sub n value. No, a sub n plus 1 value. So that's an important thing to remember. Otherwise, you're always going to be one off with your calculations. So let's not do this trial and error on this one because I think my n value is going to be very, very large. So instead, let's keep in mind that r sub n is always less than or equal to a sub n plus 1. So I'm going to put in n plus 1 in for n. And I want to make sure that this error is definitely less than 1 over 1,000 because that's what they gave us here. So I'm going to go ahead and solve this and see what I end up with. Let's see, we've got 2n plus 2 minus 1. 2 minus 1 is 1, so 2n plus 1 is less than or equal to 1 over 1,000. I'll multiply both sides of this inequality by 1,000. I'll multiply both sides of this inequality by 2n plus 1. And I'll subtract 1. And I'll divide by 2. and I'll get n is greater than or equal to half of 999, which is 499.5. If n is greater than this, but n is an integer, then the smallest n can be is 500. All right? So remember to plug in n plus 1 into here, into the a sub n value, so that we can kind of work our way back to what the number of terms is that's going to guarantee that error be less than 1 over 1,000. Same idea here. We know that r sub n is less than or equal to 1 over n plus 1. We're replacing this n with n plus 1 factorial. And again, we want to make sure that this is less than or possibly equal to 1,000. All right. Now this one is not so easy to solve algebraically, so we're going to maybe make a chart here. This is the same thing as 1 over n plus 2 factorial. So maybe I'll start with n equals 2. I'll skip n equals 1. I don't need that one. When n equals 2, 2 plus 2 is 4. 4 factorial is 24. Not big enough. When n equals 3, we get 1 over 5 factorial. 5 factorial is 120. Still not big enough. When n equals 4, we get 1 over 6 factorial, which is 1 over 720. Again, still not big enough. So when n equals 5, we get 1 over 7 factorial, and 7 factorial, I don't have memorized, but my calculator tells me is 5040. And 5040 is, in fact, small enough to get under that required accuracy of 1 over 1,000. So n equals 5 is the first value that will reach that desired accuracy. Remember, we could take these partial sums out further to get even more accurate values. So really what we're doing is we're finding the smallest value of n that satisfies the requirements